Hello, good morning dear students. Welcome back. So during class I discussed about radiant heat or thermal radiation. That is, every heated body emits heat energy in the form of wave by radiation. Means heat energy always emits or spread in all direction, transmitted in all direction from its source, that is heated body, in the form of wave through radiation process, and this heat wave is called radiant heat or thermal radiation. Okay, and it depends on some factors, that is the temperature of the body, nature of the body, and its surface also. It means if the temperature of the body is greater than that of the surroundings, then the rate of thermal emission or thermal radiation both are same, as I told in last class. That is, the radiant and the emission terms are used parallelly to understand or explain the rate of emission of heat. Okay, so if the temperature of the body is greater than that of the surroundings, then the rate of thermal radiation or thermal emission is also increases, and if the temperature of the body is less than that of the surroundings, rate of thermal radiation or emission reduces. Again, if its surface area is large, increases, then obviously its rate of thermal emission also increases, and if it less, it reduces. The nature, it means during class I already discussed, that is that if we take an uneven, it means a rough and a black surface, isn't it, at same temperature, and if we take a smooth and white surface, then the rate of emission, rate of radiant heat or rate of thermal emission is greater for the black surface in comparison to white surface. It may create some confusion because reflection and absorption is not the same. Radiation and reflection is totally two different things. We all have just grown up learning that the white surface readily reflects so much heat. Yes, but the radiation, okay, the radiator and the reflector are not two same things, because we have already learned that a good absorber can be also a good radiator also. If a body is a good absorber, then it is also a good radiator, but it is a poor reflector, and a good reflector is a bad absorber as well as a bad radiator also. Because what do you mean by good absorber and good radiator? Good radiator means the radiation of heat. It means at first the body has to absorb some heat. It means you have to capture, you have to keep some heat inside it, then it will radiate that heat. If there is no heat inside it, then how will it will be able to radiate some heat? It is just like if you want to buy something, isn't it? Then you should have enough money, isn't it? Or if anybody wants to spend some energy or want to do some work, then he or she should have enough energy inside him. Okay, if you don't have enough money to buy something, then you cannot buy or purchase that thing. It is just like that. It means a body which is a good reflector, it means if any radiant heat is incident on it, then all amount of heat will be reflected, then it cannot absorb, then it will not be able to absorb any amount of heat. Then if its total amount of absorption heat is zero, then in that case it cannot radiate any heat. Okay, and if a body can also absorb enough amount of heat, it is a bad reflector. It means suppose some amount of heat, radiant heat is incident on it, and if it is not reflect, it doesn't let the total amount of heat to reflect, only in that case it can absorb that amount of heat. So it means a bad reflector can absorb enough amount of heat, and then only then it can radiate that amount of heat, which happens exactly in case of land bridge and sea bridge. As I have discussed, in land, during daytime it gets heated very fast and very quickly in comparison to water, and because since in daytime it absorbs a large amount of heat in the daytime, because of this in the evening or at night it can radiate that amount of heat and it becomes cold, isn't it? So always remember, I have already told in the class, a bad reflector, it means which don't allow to absorb. As soon as the heat is incident on it, all amount of heat is reflected, so it cannot absorb any amount of heat. So since absorption is zero, radiation is also zero. Reflection and radiation is totally two opposite thing, isn't it? And a good absorber, it cannot reflect. It don't let any heat to go away. It will absorb. Then just like land in the evening or the night, it will radiate that amount of heat. Okay. So and surface area. Okay. So this is the nature of the surface. So that's why, since a black surface is a good absorber, so that's why it is a good radiator also. If all amount of heat will reflect, then it cannot absorb, it cannot radiate also. Okay. So now from that term, there are some related terms. Okay. There are some technical terms related to thermal radiation. Okay. So first there is the image power. It is very clear for me. The emission, the amount of emission. Okay. It is measured by total amount of radiant energy. Okay. Per unit area per second. Clear? So since we can measure it through, since it is total amount of radiant energy means since energy is measured by the total amount of work done, so per unit area per second. So from that we can clearly understand its unit, that is joule per meter square per second. Since joule per second is watt, so we can easily say its unit is watt per meter square. Very easy. Total amount of radiant energy in case of radiation, not absorption, per unit area per second. Now spectral emission power. Spectral means spectrum. You have in class 10 you have already gone through. It means when any heated body, since it emits different types of wavelengths, so there will be obviously some spectrum related to it. Since we have already learned that a band of colors, isn't it? A band of colors when forms through passing of hot light through a transparent prism, that is called spectrum. So since a heated body emits different types of wavelength, so spectrums are related to it. So that's why the term spectral emission power. We don't know which kind of wavelength, maybe different type of. So it is the radiant energy per unit area per second. Up to this it is similar to emission power. But extra term, that is per wavelength. It means we may say that is average wavelength. That is average emission power, isn't it? That is in terms of wavelength, isn't it? Radiant energy per unit area per second, but in per unit wavelength. It means since any heated body emits different types of wavelength or different types of wavelengths are emitted from a particular heated body, so there may be some. So what is the average? So the emission power per average wavelength, isn't it? That emission power is lie between lambda plus half and lambda minus half. Why? If you calculate its average, you will get lambda, isn't it? That is plus or minus half cross divided by 2 lambda by 2, that is lambda. So that is, it's the average wavelength, emission power per average wavelength, though it is not total, because emission power is the total radiant energy. Or a spectral emission power is only associated to the spectrum of definite wavelength. Okay, so we don't know, since different wavelengths are emitted, so generally we take average wavelength, isn't it? Just like temperature, we take the average kinetic energy of the molecules. Since the kinetic energy or the speed or velocity of all the molecules are not same, some moves with greater velocity, some less, some less, high, so we take an average value. So in this case we take an average value of wavelength. So again, what's the unit? Up to this is okay, radiant energy per area per second, that is watt per meter square, but that is extra term, that is average wavelength per wavelength, so that is angstrom. Okay, so watt per meter square per angstrom. Then radiant intensity. Look at the term intensity. Since all are associated to thermal radiation, as I said, all these are the related terms associated to thermal radiation. Okay, so radiant, what is the radiant intensity? Okay, radiant intensity is the total radiant or emission power. Total emission power. Okay, that is, it is related, it is generally expressed as IT. Why T? Here T stands for temperature, absolute temperature. Okay, it may be written, okay, it could have been written, it may be written like I proportional to d by 4, since it is the function of T, it depends on absolute temperature. So it is IT is directly proportional to T to the power 4, means fourth power of absolute temperature, okay, which is nothing but the mathematical expression of or statement of Stephen's law. When we will discuss about Stephen's law, we will discuss in detail about it in the next few videos, okay. We will just going to discuss about Stephen's law, but it is the absolute temperature of the body, okay. Now for spectral radiancy or emissive power, this is in terms of absolute temperature, but when, since there is a spectral emissive power, since there are, in case of thermal radiation, different radiations of different wavelengths are emitted, so obviously spectrum is associated with it. So for spectral radiancy or spectral emissive power, IT is proportional to 0 to infinity, isn't it? From 0 wavelength to, okay, from 0 to infinity, we don't know, so many wavelengths are generally emitted. So A lambda, D lambda or R lambda, D lambda. What is A lambda or R lambda? These are the spectral radiancy or emissive power at a particular wavelength lambda, within the wavelength lambda. It is the spectral radiancy. Clear? You can clearly understand. Now next term is emissivity. All are associated to emission, radiation, emissivity. Emissivity, ability to emit, isn't it? Emissivity, activity or ability to emit heat energy, to emit heat energy, which is also called relative emissive power. Relative, isn't it? Okay, so it is generally defined as, you can see, the total radiant heat by any surface at a particular temperature and at a given time, at a definite temperature, definite time, divided by total radiant heat by a black body of same surface. Why same surface? Because comparison is always done between similar objects. So the body which is taken at any definite surface area, then we will have to take a black body of same surface area, then we can compare, that is how total amount of energy, of heat energy is radiant by that body, by the surface of that body, and then how much heat energy or heat energy is radiated by a black body surface, okay, of same surface area at the same time, at the same temperature. Then this ratio is generally expresses emissivity or relative emissive power, or you may say this is the total radiant power by any body, mind it, at a definite temperature for a definite time, divided by total radiant power, we can say, by black body having same surface area as that of the body, also for the same time and same temperature. It is a constant, okay. You can see it is generally indicated by sign almost epsilon, isn't it? That is constant and which depends on the nature of the surface area. Obviously, since it is the case of radiation, emission, if it is black, it will be more, isn't it? And if it is, okay, if temperature is more, isn't it, surface area? If it is glossy and white, then it will be less, isn't it? Since it is associated to emission, radiation, as I already said, that is a good absorber is a good radiator and bad reflector, like that. And okay, so now what should be its value? That is 0 to, okay, so here its value is 0. Now since it is associated to or related to emission, just you can just imagine. So just you think and just, okay, you can think and just you can try to give the answer. So what would be, for which materials or for which surface its value could be 0, that is minimum, and for which materials it could be maximum. Since it is, okay, it is the fact of emission, so obviously it will be 0 for a, what can you say, then it is 0 for a bad reflector, isn't it? For a ideal reflector, isn't it? For ideal reflector means it will deflect all sorts of thermal radiation, so in that case it cannot absorb any sort of heat. So okay, so since it cannot absorb, obviously it is a bad absorber also, so that's why since it is emissivity, it is 0, as it will absorb only in that case. If it is able to absorb enough amount of heat energy, only in that case it will radiate or emit. But if it is a perfect reflector, it means if all sorts of radiant heat is reflected, then there will be no amount of heat energy, it will be stored inside it, then it cannot, if it cannot absorb, it cannot radiate also. So it is only possible in case of an ideal reflector. So for an ideal reflector which reflects all sorts of radiant heat, all amount of. So in this case emissivity will be 0, since emissivity or the relative emissive power is related to total amount of heat energy to radiate. If it can absorb, as I said, isn't it very easy to understand? Hope you have already understand. Okay, concept is clear. If there is no amount of heat inside it, if it cannot absorb, then later it cannot radiate or emit any heat. So only in this case, when is it possible? If it reflects all, okay, the total amount of radiant heat. So that's why for an ideal reflector it is 0. So for which materials it can be maximum? Very easy. For a good absorber, that is a good reflector means good absorber, good radiator, but a bad reflector, isn't it? It is maximum. Which body behaves as a perfect absorber? A perfectly black body, isn't it? So bad reflector, whenever any radiant heat is incident in, it will absorb total amount of radiant heat. So it means it cannot reflect. No radiant heat. Okay. All amount of radiant heat will be absorbed by it. So nothing will be reflected, and only in the case it means it is an ideal radiator, isn't it? But ideal absorber, ideal radiator means bad reflector. Okay, it will not reflect any sorts of radiant heat or thermal radiation. It is only possible, you have already learned, that is a perfectly black body absorbs all sorts of radiation, all sorts of heat, doesn't let anything to, okay, doesn't reflect any amount. So this is the emissivity. Next is the absorptive power. Since the emission, radiation, okay, depends on absorption, since before, at first absorption takes place, then emission, okay, a body at first absorb radiant heat, then it emits. So that's why obviously there will be some absorptive term. So that is absorptive power, which is related by A. Okay, everything emission E, isn't it? Emissivity E. Okay, but now it is absorptive power, which takes place before emission. This is the cause and this is the effect. If a body cannot absorb radiant heat, then emission or radiation cannot take place. So this is more important, isn't it? So it is defined as the total radiant energy, total radiant heat absorbed by a body or a surface divided by total radiant heat incident on the body. It means it is the ratio between the total amount of absorbed radiant heat by a body divided by total amount of heat incident on the body. Okay, or in the surface. Similarly, absorptive power, for which materials it can be maximum and it can be minimum. Again, it is maximum for ideal deflector, isn't it? Ideal deflector, again it is 0, same as emissivity. Ideal deflector, it will deflect everything, so it cannot absorb anything, and for a perfectly black body it is 1 because it is a good absorber. So okay, so these are some technical terms which are very important related to or regarding thermal radiation or radiant heat.